Hello everyone, my name is Rob Chp. So we'll be looking at the chapter 2 of this course, Introduction to Robotics. So without wasting time, let's just move straight to the topics that we're going to be looking at today. So in this chapter, we'll be looking at robot kinematics. And as we have seen in chapter 1, we have seen that these manipulators of this robot arm, they move. So, and to that extent, we can, carry out a kinematic study on them because they move from one point to the other. Now, so what is kinematics? Kinematics itself is the study of motion of bodies without the consideration of the forces or the movement that cause that motion. So what are we saying? We're saying that kinematics, we want to look at the motion of a body without considering what is causing that body to move. Now, in this case, we want to look at the movement of the robot manipulators, but we do not want to consider the actuators that is causing those movements. Either it is linear or causing a rotary motion. So we just want to look at how the manipulator is moving without considering the actuators that is causing such movements to take place. So robot kinematics itself is referred to as the analytical study of the motion of a robot manipulator. So like I said, our interest in this kinematics is the motion of the robot manipulators. That is the kinematic study that we want to be looking at. So the formulation of the suitable kinematic model for the manipulator requires two different spaces which is being used. So it's either you're using the Cartesian space or the Quaternion space. So this is the two spaces by which you can model, you can do the kinematic model of a robot manipulator. It's either you're using the Cartesian space or you're using the Quaternion space. But for this course, we'll be using the Cartesian space, which is the X, Y, and Z axis. That will be what we'll be considering. So the transformation between two Cartesian coordinates. Now, for every Cartesian coordinate, you're saying that at that point of coordinates, you have the X, the Y, and the Z axis at that coordinate. So the transformation or the movement from one Cartesian coordinate to the other can be decomposed into rotation and translation. So you're saying that when you're moving from one joint to the other, because at every joint you have your Cartesian coordinates on that robot arm. So the movement from one robot joint to the other, can be decomposed either into rotation or to translation. It's either there's a rotation between those two joints, or there is a linear motion inward and outward, between those two joints. Now, to represent rotation, there are several ways by which we can represent this rotation, that we can decompose the transformation between two Cartesian coordinates. So to represent the rotation aspect of it, we can either use the Euler angle, the Gibbs vector, the Clavin parameters. We can use the pulse plane matrices. We can use the axis and angle method, and we can use the orthonormal matrices, and we can also use the Hamilton's Quaternion. So we can use any of this 7 to do the representation of the rotation. So in robotics, the homogeneous transformation based on a 4x4 matrix, orthonormal matrix, have been the most often used method of all of the 7 that I listed earlier. So the 4x4 matrix, that is the orthonormal matrix method is the most common method that is being used to represent rotation, of all this listed method. This is the method that is mostly used, and that is the same method that we are going to be using also in this course. Now, the aspect that will be of interest is how do we do this decomposition. So there is two individuals in 1955, that is Dinivitz and Ettenberg. They came out with what they call the Dinivitz-Ettenberg parameters, which is the DH parameters. They came up with these 4 different parameters, which they call the link length, the angle of twist, the joint angle, and the link offset. We're going to be looking at these 4 and how do we, obtain them from our robot arm. So they came up with this 4 parameters, saying that with these 4 parameters, you can represent rotation and transformation between 2 Cartesian coordinates of a robot arm. So we'll be looking at the DH parameters, how do we obtain them, and how do we use them in solving for the kinematics problem of a robot arm. Now, the good thing about using the DH parameter is because it limits the number of unknown to 4, which makes the computational stress to be reduced, and also even the storage space. When you're using your system to work out these kinematics, using just 4 unknowns is easier to solve. It takes less storage space on your system compared to having more than 4 unknowns in this case. So that is why the DH parameter is commonly used most of the times when you're looking at robot kinematics. So when it comes to robot kinematics, they are divided into 2, which is the forward kinematics and the inverse kinematics. Some refer to it as direct kinematics and the indirect kinematics. So you can either see it as forward kinematics or direct kinematics, or you see inverse kinematics or indirect kinematics, but they all mean the same thing. Okay, so what is forward kinematics? In forward kinematics, you're saying that the calculation of the position and orientation of the end effector frame from the joint values. So for the forward kinematics, in this case, you're saying that you want to evaluate, or you want to calculate the position and orientation of the end effector frame from the joint values. Because in the case of forward kinematics, the end effector frame is already at a certain location, so you just want to calculate the position and the orientation of the end effector frame from the joint values, because for the end effector frame to be at a certain location, all the joints on that robot arm must have been at some certain value for the arm to be at that location. So for forward kinematics, you're just saying that you want to calculate the position and the orientation of the end effector frame from the joint values, or simply put, you're finding the position and the orientation of the end effector, or the 2 points, from the joint angle. So you're saying you're going from the base of the robot to the 2 points. That is the forward kinematics. So you're moving from the base of the robot to the 2 points. You want to calculate the position and orientation of the 2 points or the end effector frame, from the joint values on the manipulators that you have. Now for the inverse kinematics is just a reverse of the forward. So in this case, you want to find joint angles to set a particular position and orientation of the 2 points. Now let me explain this so that we don't mix it up. In the case of the forward, the end effector frame is already at a position and an orientation already. Haven't set some joint values. So you just want to calculate that position and orientation of the end effector frame from the joint values that you already set. But in the case of inverse, what you know is the position and orientation of the 2 points that you want that robot arm to locate. So in this case, you now need to evaluate the angles that will give you that position and orientation. So you can see here that the inverse is the reverse of forward. In the case of forward, you know the angles. You set the angles yourself. You just want to know the position and orientation of the end effector frame. But in case of the inverse now, what you have is the position and orientation of the 2 points that you want that arm to reach. However, you need now to find the joint angles that you must set to attain that position and orientation. So for inverse, you're saying that you're trying to find what particular angles to set your joint to, the joint of your robot to, for your 2 points to be at a certain position and orientation that you desire. So if you look at the two definitions, when it comes to the design of robot arm, the kinematics that is of importance is the inverse, because if you want to design a robot arm, what you will have in mind is what position and orientation do I want my 2 points on this robot arm to be operating. Once you know those coordinates in your X, in your Y, in your Z axis, you know what point on X, what point on Y, what point on Z that you want that robot arm to be operating. Now you need to find what should you set the joint angles on your robot arm to attain those position and orientation. So when it comes to design, the kinematics of importance is the inverse kinematics. Now, what are the differences in between these two kinematics for the forward and the inverse? One of the major difference is this: forward kinematics has only one distinct solution. Why is that? Because in forward, your end effector frame is already at a position based on the joint angles that you have set. So you can only have one solution in that case, because that end effector frame is already at that position and orientation. While for the inverse, you can have, depending on the design of your robot arm, you can have several solutions, several ways by which your intended position and orientation can be attained, with the same robot arm. So in that wise, inverse kinematics is more complex to solve compared to forward kinematics, because in inverse you would have several solutions, and again you begin to test those solutions to see if that solution would actually put your end effector frame at that desired position and orientation. But for your forward, since your arm is already at a certain point and orientation, there can only be one solution for forward kinematics. So what we're saying is that we have this robot arm. Let me just try to clean this off. Okay, so we have the base here. So we have, so let's say the end effector in this case is a gripper. So it uses this point to grip something. So this is a joint, this is another joint, and this is the base. So this is the base of the robot. So I'll call this place joint 1, that's J1. This place will be joint 2, that is J2. That is J2. So we're saying that for all these joints, the base J1, J2, you have a Cartesian coordinate there, which will be your Z axis, your X, and your Y, which will be perpendicular to each other. So you put this Cartesian coordinates here, another one at this joint, another one at this joint. So you're saying that the transformation from one joint to the other, using the Cartesian space, can be decomposed into rotation and transformation. So you're saying that there's a rotation between this joint and this joint, or there's a translation saying that probably there's a straight line movement in between it. So that is what can happen. So is this rotation now that is being expressed using the orthonormal 4x4 matrix? So that's where your DH parameter comes in, which is your alpha I, which is your twist, angle of twist. So your AI also, your AI, sorry about that, let me just move this away from here. So your AI, which is your link length, and also you have your DI, which is your link offset. Then you have your theta, which is your joint angle. So these are your 4 DH parameters: your alpha I, which is your twist angle, your AI, which is your link offset, sorry, your link length, your DI is your link offset, and also your theta, which is your joint angle. So just an illustration, we can see here that for forward, you are moving from joint space to the Cartesian space, and for your inverse, you're moving from the Cartesian space to joint space, because the position and orientation of your 2 points is in Cartesian space, because you always have the position and orientation of your 2 points in X, Y, and Z axis. So you are moving from there back to joints, which are in joint angles, and for forward, you are moving from joint angles to Cartesian space. So that is just about that. Okay, so for the inverse, there are 2 methods by which the inverse kinematic problem is being solved, which is using the analytical method or the numerical method. So it depends on which one. However, the analytical method equally is divided into 2, where you have the geometric approach and the algebraic approach. So under the analytical method of solving the inverse kinematic problem, you have 2 approaches: one geometric approach and the other one, which is the algebraic approach. But of these 2 approaches for solving inverse kinematic problem under the analytical method, the most beneficial one that can solve kinematic problem, inverse kinematic problems of degree of freedom that is more than 2, is the algebraic approach. It's the most commonly used because it can solve complex inverse kinematic problems. Anyway, let's look at the DH parameter proper in this case. We have already talked about the DH parameter being 4 different parameters, which is having the alpha I, which is the twist angle, having the link offset, that's the AI, the link length, which is the AI, and the DI, which is the link offset, and also the joint angle, which is the theta. So like I said, these 2 German guys, Dinevit and Ettenberg, in 1955 developed this notation for assigning orthonormal coordinates frames to a pair of adjacent links in an open kinematic chain. So they are the one that came up with these 4 parameters that I mentioned. So the procedure involved finding the link coordinates and using them to find the 4x4 homogeneous transformation matrix composed of 4 separate submatrices to perform transformation from one coordinate frame to its adjacent coordinate frame. So what are they saying in essence? for every coordinate frame where you have the Cartesian coordinate of z, x, and y, the movement from there to the next one, can be represented using these 4 parameters. And from these 4 parameters, you have your submatrices that you'll be using to solve the kinematics problem of that very robot. Now, so most industrial robots manipulators are open loop kinematic chain consisting of the base, joint, links, and an end effector. So what do we mean by an open kinematic chain? We're saying that you have a base, you have the joints, you have the links, and you have the end effector. So there's no link between the end effector and the base, so it's open. It's an open loop kinematic chain, so there's no link between the end effector back to the base. So that is why it is regarded as an open chain, an open loop kinematic chain. So the ability to control a robot end effector in 3-dimensional space requires the knowledge of a relationship between the robot joints and the position and orientation of the end effector. So before you can control a robot end effector, because the whole idea at the end of the day is to control the end effector, because it's the end effector on your robot manipulator that actually does the work, and that is what you want to control its movement through the movement of the manipulators. So the control of the robot end effector in 3-dimensional space, meaning to control it in your x, your y, and z axis, requires the knowledge of the relationship between the robot joints and the position and orientation of the end effector. Without that, there's no way you can, control the robot end effector successfully without knowing how the joints and the position and orientation of your end effector, how they affect each other. And that relationship requires the use and an understanding of the rotation matrix and the translation vector. We already said that the transformation between 2 adjacent coordinate frames can be decomposed into rotation and translation. So to work with robot kinematics, you need to understand and use the rotation matrix and the translation vector. Okay, so this is just showing the procedure for the TH parameter. So you first of all locate your robot arm. This will still be explained in a better way. This is your robot arm. Then the next thing is that you locate the joint. Now, the notation we use for the joint is O, and the base joint will be joint OI minus 1. The next will be joint OI. The next will be joint OI plus 1. The next will be joint OI plus 2, and on like that. Now, this I is just iterative. It's starting from 1. So if you say joint OI minus 1, that means joint O1 minus 1. So that will be joint O0, that means that is the base joint. And this joint OI will now become joint O1. And this one of OI plus 1 will now be joint O2. And on like that. So the next thing is for you to determine the joint, if the joint is rotating or translating. If it is rotating, you represent that by theta. So that will be theta 1, theta 2, theta 3, and all of that. If it is translating, then that will be your DI instance. That will be your D1, D2, D3, and all of that. We'll see how this has been done in a practical way. So for your base frame, you set your Cartesian coordinates, your Z, your Y, and your X, So because this is our base frame, so this will be Zi minus 1, Yi minus 1, Xi minus 1. So when I is 1, that will be Z0, Y0, and X0. So and you move to the next joint, you do the same. The next joint, you do the same until you get to the wrist of your robot arm. And from there, you form a table of your DH parameter. The number of axes that you have, you list them. Then your twist angle, your link length, your link offset, and your joint angle for every transformation from one adjacent coordinate to the other. You find the value of each of them in these columns. So let's see how this is being done in a more practical way, so that we can get the understanding of this DH parameter that we're talking about. Now, the procedure for the DH convention is what we'll be looking at now, so that we understand it properly, because there are some rules that is being used to set these frames to your links. So those are what we'll be looking at practically. Like I said, there are 4 DH parameters. Your AI is your link length, your alpha I is your link twist angle, your DI is your link offset, which is for your prismatic movement, and your theta I is the joint angle for revolute joints. So let me just go to the whiteboard to show us how we do this in a more practical way. So if you go through the notes, you will see that the first rule here is you assign your ZI-1 axis to the actuation of the joint I. We'll explain that so that you understand what we're saying. So, because we are using the Cartesian space, so we're going to be working with the Z, the X, and the Y axis. Now, so how do we assign our Z axis? How do we assign our X? How do we assign our Y? Now, you always assign your Z for any joint on your robot in the axis of actuation of that joint. So you're saying that if this is my joint, if I have let me say this is my base of my robot. This is my base of my robot, and I'm being told that this base is rotating in this way. Rotating, is this clockwise? I think that's clockwise. So where am I going to put my ZI-1 for the base? Where am I going to put my XI-1? Where am I going to put my YI-1? So you always assign your Z in the axis of actuation of that joint. So since I know that this joint is rotating in this way, then my Z axis will be in this direction. It can either be going up, so this will be my ZI-1. It can either be going up, or I can put it down in this way. It's still the same thing. ZI-1. So that is the axis of actuation of this joint. Let's say, for instance, it is looking like this. It's rotating this way. Okay, let's even say it's rotating this way in this case. In this instance, my Z axis will be like this. This is where my Z axis will be, because it is rotating in this way. So it will be in line with the axis of actuation of that joint. That is how you set your Z axis. Now, for your X, you always assign your X such a way that it is perpendicular to and intersect with your ZI axis. So you're saying that since you have your Z already, your X would be perpendicular at 90 degrees to it. So your XI could either be in this way for this one, XI-1, or in this direction, XI-1. In both ways, you can see that this X is at 90 degrees to this zi minus 1. And for this one, it will be in this way. X, if you look at it, it is perpendicular. This will be my x in this case, xi minus 1 in this case. So it will be perpendicular to it, or I can take it into the page like this, x I minus 1 in this case. So once you assign your z-axis in the axis of actuation of that joint, then your x will always be perpendicular to your z-axis. So left for your y, so you derive your y using the right hand rule, but we will explain this in subsequent frames. So here is just the image of your right hand rule. We can see here that your thumb represents your z-axis, whereby it is your first finger here represents your x, while this one represents the direction of your y. So if you just put this right arm parallel to this, in this case, you will see that if my thumb is here and this is my x, then my y definitely will be going in this direction. In this case, it will be going in that direction. This is where my y I minus 1 would be. And if I'm doing it for this very one, then my y will be somewhere here. In this case, this will be where my yi minus 1 would be in this case. So I haven't looked at the rules of assigning these frames to the links. So we look at how do we assign these frames to the base, to the two frame, and on like that. So let's assume you have the base of a robot in this way. This is the base of your robot. Let me just clean this off here. So you have the base of your robot in this way, and you are being told that it is rotating in this direction. So you assign your z in the axis of actuation of that very joint, which will be this way. So this will now be your z I minus 1. So we are looking at the rule 1 for base frame in this case. So that will be your z I minus 1, and you assign your x perpendicular and intersecting your z I minus 1. So I can either put my x here, or I put my x into the page in this way. So I can either put it here or here, depending on where I want to put it. So this is my xi minus 1, or I put it outside the page here as xi minus 1. Also, you can put it in this way. You can either put it in this way, this way or that way, depending. Or you must ensure that it must be at 90 degrees perpendicular, and it must intersect, it must touch your z minus 1 in this way. So once this is done, what you just need to complete this to determine where your y would be is to complete this using your right hand rule. And if you recall the diagram that we used the other time, so if you make this thumb parallel to your z and this fourth finger parallel to your x, the only way your y could go is to go in this direction, something like this for your yi minus 1. So that is how you assign your frames to your links to your base frame. That's how you do your coordinates on your base frame. This is for the base of the robot, which is the first rule that we're considering here, which is this. That is what we have done. So Z0 is in the axis of rotation or translation of that joint. This is where your Z0 is. So your x naught is set as convenient. Since this is the base, you can set it anywhere, but you know that your x, following this rule here, your x has to be perpendicular and must intersect with your z. So it's here. So if you use your right hand rule to complete it, your y will be coming in that direction. So for your two frame, how do you assign this coordinate to your two frame? So let's go back to the whiteboard and see how we do that. Now let's assume we have our two frame. In this case happens to be a gripper, so that we can have all the components of our coordinates. Now if your two frame happens to be a gripper, your z-axis will be in the approach direction of your tool. In this case, this tool is facing this way, so my z-axis will be in this way for this two frame. Sorry, that's z, not y, for this two frame. And so far my two frame is my last frame, so it will be zn. So that is the last frame on that robot. So that's why it is zn, not zi minus 1 or zi or whatever it is. Now if that is the case for my two frames, so where will my y in this case be? So my y will be in the sliding direction of my gripper, because this gripper will be going inward and outward to hold whatever it is. So my y will either be in this way or in this way. This is where my y would be. That I put it this way or I put it that way. So this will be my yn, or I can put my yn here. So for the 2 points, you set your z in the approach direction of your tool and your y in the sliding direction of your tool. So to find out where my x will be, we're just going to use the right hand rule again. If I match that same right hand that we used earlier, if I match it in this way, if I match it with this, my x will be going either downward in this way, or I can try to put it upward in this way for my xn. So using the right hand rule to complete where my x will be for this very frame, which is the two frame in this case. So for the two frame, you first of all assign your z in the approach direction of your tool. The next thing you assign is your y in the sliding direction of your tool, and then your x using the right hand rule to complete it. However, if you have a tool that is not a gripper, maybe in this case it's just a welding torch or a spray painting, in that case you won't have a gripper like this. So you equally assign your z in this approach of that same tool. Now your x could be assigned, perpendicular to your z in any way you want to put it, and you can use your right hand rule, to complete where your y would be. That is for 2 point that is not a gripper. But if your 2 point is a gripper, you follow this order: your z in the approach direction, your y in the sliding direction, and your right hand rule to complete where your x will be for the two frame as a gripper. But the two frame is not a gripper, if it happens to be just a spray painting gun or a welding torch, in that case you still put your z in the approach direction. However, your y and your x, you will just use the right hand rule to set your y, haven't set your x perpendicular to your z axis in this case. So that is how you deal with your two frame. So let me just clear this canvas and let's move on to the next one. So the next one is the rule 2 case 1. Rule 2 case 1 is when your zi minus 1 and your z axis are not coplanar. So what is zi? What is zi minus 1? What is zi? You're saying that when your previous coordinate frame and the adjacent coordinate frame when the z that you have assigned are not coplanar. So what are we saying here? Let me just use the whiteboard to explain. Now, you have already, for every robot that you're dealing with the kinematic modeling, is the z-axis of all the joints that you first of all assign. So let's say you have already assigned for a certain joint zi minus 1 in this way, and my x for that joint is in this way, xi minus 1, and this is where my y for that joint is facing, yi minus 1. And then the next joint, your z, because that is the actuating axis of the joint, is facing this way. So this will be my zi, and this is just a dotted line showing that it's on the manipulator. So this is zi minus 1 that you have already assigned in the actuating direction of this joint, and also zi that you have already assigned in the actuating direction of this joint. So if this is the case, that your zi minus 1 and your zi are not coplanar, which means they are perpendicular to themselves. Because if you look at it, this zi and this zi minus 1 are perpendicular to each other. You can just say your zi minus 1, your zi is something somewhere here, just to show that they are, perpendicular to each other. So where do you assign the x of this zi? Now you're going to assign the x of this zi perpendicular to this zi axis, and also intersecting with it, and you must ensure that it's equally perpendicular to this zi minus 1. So what are we saying? When you're assigning the xi of this coordinate frame, it must be perpendicular to zi and also to zi minus 1. So the only way you can assign an xi that will be perpendicular to zi and zi minus 1 is only in this direction. It's only in this direction that you can assign an xi that is perpendicular and intersecting with zi and also perpendicular to zi minus 1. Because if you look at it, xi is perpendicular to zi, and if you take back this xi here, is equally around this place, is equally perpendicular to zi minus 1. So you must ensure that when you're setting your xi axis, for the instance where your zi minus 1 and your zi are not coplanar, which means they are at 90 degrees to themselves, when your zi minus 1 and your zi is at 90 degrees to themselves, when they are not coplanar, then you must set your xi in such a way that it is at 90 degree and intersecting with zi and also perpendicular to zi minus 1. So you can't put your xi, in this way. If you put your xi here, if you look at it, it is perpendicular to zi, true. However, if you take it backward, you can see that it is parallel to zi minus 1. So to that extent, you cannot put your xi in this way, and you can't equally put your xi up like this, because you put it up in this way, put your xi here, though it is perpendicular to zi and is intersecting with it. However, if you take it back to zi minus 1, it is parallel to it. So that is why you will not be able to choose these directions for the coordinates of your xi in this case when your zi and your zi minus 1 are not coplanar. So that is for rule 2 case 1. So for rule 2 case 2, in this case you have zi minus 1 and zi axis when they are parallel to each other. When they are parallel, so you're saying that you've already assigned your previous z axis in this way. Let me just use this diagram again. So you have your z high minus 1 here, and here you have your y I minus 1, and you have your x I minus 1 here. So you now have, so this is joint OI minus 1, you know. So you now have your next joint is such that when you assigned your ZI, it is parallel. It is parallel to your ZI minus 1. So this will be joint OI in this case. And the next joint will be joint OI plus 1. The next one will be joint OI plus 2, and so on. So if this is the case that your ZI and your ZI minus 1 is parallel to themselves, so where would be the appropriate position for your XI in this case? Know that your XI would always be perpendicular and intersecting with your ZI. However, you must also know that your XI must equally be perpendicular to your ZI minus 1. So where can you put it? If you look at it, if you put your XI here, right, it is perpendicular to ZI, and it's also perpendicular to ZI minus 1. If you put it here, right, it is perpendicular to ZI and also perpendicular to ZI minus 1. If you put it here, it is perpendicular to ZI, because this is 90, and also perpendicular to ZI minus 1. So what will actually determine where you are going to put your XI minus 1 in this instance? What will now determine is that you want to put your XI in a position such that your DI, because your DI in your DH parameter is the perpendicular distance between your XI minus 1 and your XI. So your DI is the perpendicular distance between your ZI minus 1 and your ZI. So in this instance, you can put your X in a position that would ensure that there is no perpendicular distance between your XI minus 1 and your XI, so that the instance of your DI in this case would equal to 0. So I'll put my XI in this way. It is perpendicular to ZI, intersecting with ZI, and also perpendicular to ZI minus 1. And there's no perpendicular distance between this XI, you know, and this XI minus 1, because at the end of the day, XI and XI minus 1 are looking like this. XI minus 1, and this is XI. This is what they are looking like. There's no perpendicular distance between them. But if I had assigned my XI to be here, in this case, I will have XI perpendicular and intersecting with ZI minus 1, with ZI, sorry, and also perpendicular to ZI minus 1. And there will be a perpendicular distance between XI minus 1 and XI, which will give me a value for DI in this case. But because I want to make my matrix at the end of the day less complex, so I'm going to assign my XI, you know, in this instance where I have my ZI and ZI minus 1 parallel to themselves, in a position that would make my XI and my XI minus 1 not to have any perpendicular distance between them. So I'll put it in this direction. So that is for root 2, case 2, which is what we have done here. So for root 2, case 3, in this case, you have your ZI minus 1 and your ZI when they intersect each other, when they are intersecting. So where is your XI going to be? So let me equally move to the whiteboard. Let me just use this side. Let me clean this off here. Let me clean this off and let me use this side. So when you have your xi and xi minus 1 intersecting, so let's say you've already assigned your xi minus 1, your zi minus 1 in this case. This is your joint OI minus 1. So you have your zi minus 1 here. This is your yi minus 1, xi minus 1. And you now assign your, sorry, let me just clean this off. You now assign your zi, and you found out that your zi is intersecting with your zi minus 1. In this case, this is where your zi is in this case. So these joints here, these joints here, I'll just clean this off, make it readable. So these joints here is your joint OI. This joint here, your joint OI. So this is where your ZI is, and is intersecting your ZI minus 1. So where can you put your XI? You recall that your X will always be perpendicular and intersecting with your Z. So in this case, my Z is ZI. So I'll put my X in a way that is perpendicular and is intersecting with my ZI. And also it must be perpendicular to my ZI minus 1. So the only place I can put it in this case is to put it here, or put it back here. Did I put it here, XI, or I put it here, XI? It is perpendicular to this ZI, intersecting with it. And if you take it further backward here, you can see that it is also perpendicular to my ZI minus 1 in this case. So that is for rule 2 case 3. So that is how you assign all these coordinates to your joints. Now the DH parameter, we already said there are 4. You have the alpha, which is the twist angle. You have the link offset, which is your AI. You have the DI, which is your, link length AI, DI link offset, and you have the theta, which is your joint angle. So let's see what they are. So your, let me just go back. Your AI is the distance between your ZI minus 1 to ZI measured along your XI axis. So if you look at this, if you look at this diagram here, let me just enlarge this very well. Okay, it's not really doing what I want it to do. But if you check your notes, you will see that your AI is the distance from your ZI minus 1 to ZI measured along your ZI, your XI axis. That's how you determine your AI. Or simply put, your AI is the perpendicular distance between your ZI minus 1 and your ZI. Your alpha I is the angle from your ZI minus 1 to ZI measured about your XI axis. So to determine what your alpha is, what your twist angle is the angle from your zi minus 1 to zi measured about your xi axis. And for your di is the distance from your xi minus 1 to xi measured along your zi minus 1 axis. So distance between from your xi minus 1 to xi measured along your zi minus 1 axis. While your theta is the angle from xi minus 1 to xi measured about your zi minus 1 axis. So okay, let's still continue. Now, what will happen at the end of the day? Okay, let's first of all do an example whereby we evaluate all these DH parameter for a certain robot arm. So, but before that, this matrix here is the forward transformation model for your forward kinematics model. This is the matrix. So everything you have on this, the first three column, this column, this column, and this column is your rotation, while what you have on the fourth column is your translation. If you recall, we said that the transformation from one coordinate frame to the other can be decomposed into rotation and translation. So this is the 4x4 matrix at the end of the day, and the first three columns here represent the rotation, while the last column here represents the translation. That is what is being depicted here. Your R naught to N and your D naught to N. So this is your translation, and the first three column is your rotation. So all this C theta 1, that is cos theta 1. Sorry, this C theta I, that's your cos theta I. You know, this minus S sine minus S theta I is your sine. C is your cos. So that just to make it readable, so that it won't be too bulky, too complex to see. So your C is your cos, your S is your sine. So that is what this matrix represents. This is the forward transformation matrix. So the first thing you do, get your DA parameter, and for every transformation you get your sub matrix, your sub forward transformation matrix. So let's do an instance so that we can understand all of this in a much better way. Okay, so here is it. We have this robot arm here, and we are already told that this base rotates, you know, in this wise. This joint here also rotates in this wise. And also there's another joint here which equally rotates in this wise. And also we have another joint here which equally rotates in this wise. And we have another joint here which equally rotates in this wise. And here we have the sixth axis, which is for the 2 points. In this case, the 2 points is not a gripper, so it's just pointing forward. So how do we assign all of these Z, X, and Y to all these joints? So the first thing is you start from the base. The base is here, and you always assign your Z axis first. So your Z axis will be assigned in the actuating axis of that joint. Since I know that this joint is rotating in this way, then my Z axis would be in this way. This is where my Z axis would be for this base joint. So this will be my Z I minus 1, which will be my Z naught in this case, because my base is 1 and 1 minus 1 will be 0. So where is my X going to be? I would assign my X perpendicular to perpendicular to my Z naught, at the same time intersecting with my Z naught, but I want to make it parallel to where my 2 points is facing. So I'll be assigning my Z here, sorry, my X naught here. If you look at it, this is my X naught. X naught here is perpendicular to my Z naught in this way, and it's intersecting with my Z naught as well. And I'm making my Z naught to take a direction that is parallel to where my 2 points is facing. You know, that's just what I've done here. So to complete this with the right hand rule, if you take the right hand rule, then your Y should be coming somewhere here for your Y naught in this case. So that's for the base. Now the next thing we're going to do is to assign the Z for the second axis here. You go to the third axis, you do the same. The fourth axis, you do the same. The fifth, you do the same. And the sixth, you do the same. So here I can see that this joint is actuating in this way. So this is where my Z axis would be for this one. This would be my Z1 in this case, because this will be my Z1. This is my actuating direction. So this will be my Z1. Also, this third axis, the actuation is in this way. So in that wise, this will be my, you know, Z2 in this case. This will be my Z2 in this case. Now my Z2. And my fourth axis, the actuation is in this way. So it will be in this direction for my Z3. In this case, this is my Z3. Let me just clean this off and write it properly. So this will be my Z3. So that's my Z3. Now for my fifth axis, the actuation is in this way. So this will be in this way. So I can either face this side or face this side, depending on where I want to face it. So this will be my Z4 or Z4 in this way. In this way. Z4 in this way. Then it's left for my sixth axis, which is my 2 axis. And we said for your tool, your Z will always be in the approach direction, and the approach direction of this tool is equal in this way. So I have my Z5 here in this way. So my Z5. So 0, 1, 2, 3, 4, 5. So that completes for all the 6 axis that I have. Now, you know, we are here to fix the X for Z1, Z2, Z3, Z4, and Z5. Okay, so for Z1, where will the X be in this case? Now, if you recall the rule that we talked about, this is a case whereby your Z0, which is your Zi minus 1 here, and your Zi are intersecting. If you recall when we talked about our rules. So that is the case of rule 2, case 3. That is the case of rule 2, case 3. So where are you going to assign your X in this way? You assign your X in a way that it is perpendicular to your Z axis and intersecting with it, and at the same time perpendicular to your Zi minus 1 axis. So in this case, I will be assigning my X X1 in this way. This would be where my X1 would be. If you look at it, it is perpendicular to my Z1 and intersecting with my Z1. And at the same time, if you bring it back down here, it is perpendicular to my z0, which is my zi minus 1 in this case. So we move on to z2. Where would the x be in this case? If you look at the rules, you will see that this is the case whereby your zi minus 1, which is your z1 in this case, and your zi, which is your z2 in this case, where they are parallel. You can see that they are parallel to each other in this case. So you want to assign your x for your x2 now in a way that it is perpendicular and intersecting with your z2, at the same time perpendicular to your z1, but it should in a way eliminate perpendicular distance between your x1 and x2. So the best place to put this in this case, because actually you can put it up here, saying this is my x2. You can put it down here, say this is my x2. You can put it here, say this is my x2. You can put it back here, say this is my x2. But what will actually govern where you're going to put it, because any of this direction is perpendicular to this z2 and is intersecting with it, and if you bring it back down here, is equally doing the same thing. But the best place to put it so that you would eliminate any form of value for di in this instance is to put your xi, which is your x2 in this case, up here. Is where x2 should be. Doing this would, you see, it is 90 degrees to this and it's intersecting with it. If you bring it back down, if this robot arm moves in this way, it will equally be at 90 degrees to this zi, but you will see that the relationship between xi, which is x2 in this case, and xi minus 1, which is x1, is something like this. This is my x2 and this is my x1. So meaning that my di for this instance will be 0 because I'm not having any perpendicular distance between them. But if I've chosen my x2 to be in this way, you understand, to be in this way, what will happen is that I will have something like this between my x1 and x2, and that will give me a value for d1, which would be something, maybe let's say variable q in this case, variable q in this case. And I don't want that to happen because I don't want to have a complex matrix at the end of the day. So that's why I'm using the advantage of the rule that we talked about to eliminate my d, which is my link offset, to have a value in this case. So that is why I'm putting my x up there. So that's my x2. So where is my x3 going to be? So let's look at it again. My z3 and my z2, what is their relationship? This is a case whereby they are not coplanar. This is a case whereby they are not coplanar. That is root 2 case 1. So where am I going to put my x3 to ensure that it is perpendicular and intersecting with z3 and at the same time perpendicular to z2? The only place I can put it is to put my x3 up here as well. This is where my x3 will be in this case. This is where my x3 will be. Why? Because putting it here will be perpendicular to x3, to z3, intersecting with z3, and at the same time, if you take it backward here, it is equally perpendicular to my z2. So this is the safe place to put my x3, or you can equally put it down here if you want to. I put it down here and say this is where your x3 is. It's equally the same thing, but I decided to put mine up there. So that's for my x3. So for my x4, so this is my z4. My z4 and my Z3. This is an instance of also a coplanar instance as well. It's a coplanar instance as well. It's still your rule 2 case 1 instance in this case. Still your rule 2 case 1 instance. So I will put in my x4 in this case, where it is perpendicular and intersecting with Z4 and also perpendicular to Z3. So this is where my x4 also will be here. Putting my x4 here, you can see it is perpendicular and intersecting with my Z4 and also perpendicular to my Z3. So that is where my x4 would be, equally going up in the direction of my x3. So where would my x5 in this case be? So my Z5 and my Z5 and my Z4, this is an instance where my xi minus 1, which is Z4, and my xi, which is Z5 in this case, where they are perpendicular to themselves. If you look at it, this is my Z5 and this is my Z4. So they are perpendicular. And in that wise, I will assign my x for my x5 now in a direction that is perpendicular and intersecting with my Z5, at the same time perpendicular to my Z4. So in this case, I'm going to put my the Z5 here in this case is the 2 points. Is the 2 points in this case. So I'm just going to use the right hand rule to complete it, since it's not a gripper. If it's a gripper now, I will have used my y in the sliding direction and my right hand rule to complete my x. But since it is not a gripper, we have already assigned our Z5 in the approach direction of the tool. So it's just to assign the x. So in this case, I will still follow the x perpendicular intersecting with my Z5 and also perpendicular to my Z4. So to that extent, you would see that your x5 also would be either you put it up here or you put it down, because in this way it is perpendicular to your Z5 and also perpendicular to your Z4. So that is just to show you, and let's look at the example in the notes also to make more sense of it. So the example here said determine the DH parameter and the forward kinematics expression for the robot arm shown below. This is the robot arm in this case. So this is the base of this robot, and this is another joint 2 rotating in this direction, joint 1 in this direction, and this joint 3 here showing this arrow is telling you that this is a linear joint, prismatic joint, which means it's going inward and outward, and the 2 points here is a gripper in this case. So that is the robot that we have, and the distance from the base to this joint 2 is 3 meters, whereby the distance from this joint 2 to the wrist of your robot here is L3, as is being given here. So you assign your Z0 in the rotating direction of your tool, of your joint. So since it is rotating in this way, so the Z0 is facing upward, Z0, and you assign your X0 in this case. perpendicular and intersecting with your Z0. Because this is the base, I'll be making it parallel to where my robot arm is facing. So that is why it is being assigned in this direction for my X0. So if you use the right hand rule to complete this, your Y0 will be in this direction. So this is joint 2. Now, the first thing is to assign your Z-axis. That will be your Z1. So far, it is actuating in this way. So your Z1 is in this direction, in the axis of actuation of that joint. This is your Z1. Now for your prismatic joint, this is your joint 3, which happens to be your Z2 in this case, is going in this actuating direction, which is going outward. So this is where your Z2 is in this case. Now for your 2 points, this is your Z3 in this case. The Z will be in the approach direction, which is, this is the approach direction of the tool. Because this is a gripper, you have the Y3 in the sliding direction. So either you put your Y here or you put your Y in this way. So to complete this X3, just use your right hand rule. So far, this is your Z, your Y is going this way, then your X is going upward. This is your X3 in this case. So it's left for us to determine where X2 should be and where X1 should be and where your X2 should be. So to determine where X2 should be, if you look at the relationship between your Z0 and your Z1, you can see that in this case, if you transfer your Z0 up here, so this is a case whereby your X0, your Zi minus 1 and your Zi are perpendicular to each other. You know, they are perpendicular. So you can select your X1 in a way that it is perpendicular and intersecting with your Z1, and also perpendicular to your Zi minus 1, which is your Z0 in this case. So the best place to put it is that you put your X1 in this direction, as it's been done here, or you put it into the page to the other side. It's still the same thing. In that wise, it is perpendicular and intersecting with your Z1, and also perpendicular to your Z0 here, because this line here is perpendicular to this Z0 in this case. So that is why your X1 is here. So you can use your right hand rule to complete it. You see that your Y1 will be coming downward as it is shown here. Now to determine your X2, what is the relationship between your Z2 and your Z1? Also, you can see that your Z2 and your Z1 are perpendicular. They are at 90 degrees to each other. So in that case, you put your X2 in a location whereby it is perpendicular and intersecting with your Z2 and also perpendicular to your Z1. And where that can be is to be here, X2. In this wise, it is perpendicular and intersecting with Z2 here, and also perpendicular to Z1 in this case. So with that, you have done all the assignment of the axis for your Cartesian space. So the next thing is to write the DH parameter after you have assigned all the axes. Now, you just create a table in this way. So you have your number of joints. There are 3 joints, joint 1, joint 2, joint 3. You have your alpha, which is your twist angle, your AI, which is your link length, your DI, which is your link offset, and your theta I, which is your joint angle. So how do you determine these values from this axis that you have stated? So for joint 1 is your transformation from the base to Z1, from Z0 to Z1, from 0 to 1, from 1 to 2, from 2 here to 3. So 0 to 1, 1 to 2, 2 to 3. So from here to here, from here to this point, from this point to this point. So that is what you have here. Now, what is the alpha? What is the twist angle for the transformation from Z0 to Z1. How do you evaluate that? We already said that your twist angle, which is your alpha, it is the angle that is measured from your Zi minus 1 to Zi about your Xi axis. So what are we saying? What is my Zi minus 1 in this case? And what is my Zi? My Zi minus 1 here is Z0. And the Zi here is Z1. So if you look at it, Z0 and Z1, they are at 90 degrees to each other. So measured about the Xi axis. So the Xi in this case is my X1. So about that axis. So if you bring up your Z0 here, so angle from Z0 to Z1 about the Xi, which is X1 in this case, axis. So Z0 comes up here, Z1. If you go from Z0 to Z1 now, that will be 90. However, you can see that it is opposite to the direction of rotation that is given here. It is opposite to the X1 direction, because if you measure Z0 to Z1, if you bring Z0 up here, you measure it Z0 to Z1, which is 90 in this case. However, your X1 is facing another direction, because Z0 to Z1 will be in this direction and your X1 is in this direction. That is why it is minus 90, because your alpha is the angle from your Zi minus 1 to Zi measured about your Xi axis. So that is why it is minus 90. So what is your A? Your A is the distance. Your A is the distance from your Zi to Zi, from your Zi minus 1 to Zi measured along your Xi axis. So distance from your Zi minus 1 to Zi, so Z0 to Z1 measured along my Xi axis. The Xi in this case is X1. So you can see that we can't measure any distance from Z0 to Z1 along this X1 axis. Or the easy way to do it is that you can see that there is no perpendicular distance between your Z0 and your Z1, because if you do it, you see that your Z0 will come up here and there's no perpendicular distance between them. So your AI in this case, which is your A0, will be 0. For your D is the distance from your Xi to Xi minus 1 to Xi measured along your Zi minus 1 axis. So in this case, what is my Xi minus 1 is X0 in this case, and my Xi is X1. The distance is being measured along the Zi minus 1 axis, which is the Z0, and this is the axis of my Z0. So distance from this point to this point along this Z0 axis is 3m. It is 3 meters in this case, and that is why this is 3. Distance from my Xi minus 1 to Xi measured along my Zi minus 1 axis. So the Zi minus 1 here is Z0, and the Xi minus 1 here is X0, and Xi here is X1, and this is along Z0 axis, and that length is 3. So that's why this is 3. So theta is the joint angle, and theta is the angle from my Xi minus 1 to Xi measured about the Zi minus 1 axis. So Xi minus 1 to Xi about Zi minus 1 axis, which is Z0 in this case. And we can see that there's no way we can measure any angle from X0 to x1 about z0 axis. Or you can just see it whenever your xi minus 1 and your xi is parallel to themselves, your theta is 0, because if you look at it, xi, which is x1 here, and x0, they are parallel. So once they are parallel, then your theta is 0. So on to the next one, which is this. So your transformation from z1 to z2. From z1 to z2. So from z1 to z2, twist angle, which is the angle from zi minus 1 to zi measured about your xi axis. In this case, the zi minus 1 is z1 and the zi is z2. If you look at it, they are at 90 degrees to each other. This is z1, this is z2, measured about xi axis, which is x2 in this case. Now we can see that the axis of x2 is upward like this, and x2 to x1 is going in this way, x2 to x1, x2 to x1, about x2 axis, but it is x2 is going upward. So because this is going this way and this is going upward, the 90 is negative 90. So that's why that is so. Now link length is the distance from zi minus 1 to zi, that is being measured about the xi axis. That is for AI, which is A1 in this case. So there's no distance from Z2 to Z1. They are on this same point, something like this. So that is why that is equally 0, because there's no distance I can measure along x2 axis between Z2 and Z1. X2 is going in this direction and Z2 and Z1 are in this direction. So you can't measure any distance between this Z2 and Z1 in this direction. That is why this is 0. Now D is the distance from xi minus 1 to xi measured along the zi minus 1 axis. So in this case, my xi minus 1 is x1 and xi is x2, and the zi minus 1 in this case is z1. There's no way I can measure any distance between these two, x2 and x1, in this z1 direction. So that is why this is 0. Now theta is joint angle, which is the angle between xi minus 1 and xi measured about zi minus 1 axis. So the xi minus 1 in this case is x1 and the xi minus xi in this case is x2, and the zi minus 1 in this case is z1. So the angle between x2 to x1 is 90, as you can see here, is 90, measured about the xi minus 1 axis, which is in this direction of z1. So this is going from here to here, 90. However, the axis of z1 is in this direction. That is why this is equally minus 90 here. So for the last transformation from 2 to 3, so from z2 to z3 in this case, so z2 to z3, so we can see that z2 and z3, they are parallel, and to that extent there's no way we can measure any angle between them in the direction of xi minus 1. That is why this is 0. Also x2 and x3 are parallel. There's no way we can measure any distance between them in the direction of x2. So that is why this is equally 0. Now x2 and x3, that is xi minus 1 and xi, your D is the distance measured between xi minus 1 to xi along zi minus 1 axis. So this xi minus 1 here is x2, and the xi here is x3, and the zi minus 1 is z2. So distance between x2 to x3 in the direction of z2 is L3 in this case. So that's why this is L3. So theta is the angle between xi minus 1 and xi, measured about the zi minus 1 axis. But if you look at it, x3 and x2 are parallel, so your theta is 0. So that is how you fill up the DH parameter in this case. So the next thing you want to do is now to do the forward kinematics. So what you're going to be having is that you're going to form a submatrix of this transformation, and this transformation. So you're going to have 3 submatrices in this case. So if you look at it, this is matrix 1, matrix 2, matrix 3. If you go back to the forward transformation matrix that I showed you, this is forward transformation matrix in this case, and if you just look at the page of your notes where we already have the DH parameter of all of the parameters for the transformation from 1 to 2, 0 to 1, 2 to 3, 1 to 2. So the theta 1 in this case is, the first theta here is this 0, that's theta naught in this case, because this is c theta I minus s theta 1 c alpha I, and on like that. So if you look at the right side of the screen, this is the DH parameter that we just obtained on the right side of the screen here. So this is on the left here, and to the right here you have the forward transformation matrix model. So you're going to create for every transformation you have here, you're going to create its own matrix. So in this case, you're going to have a sub matrix for this row, and also this row. So in this case, you have c theta I. The theta in this case is theta naught for this row, and the value is 0. So what is cos 0? You find that out. So that's why you have c1 here. So you have here c1. Also minus sine theta cos alpha I. Alpha I in this case is minus 90. You find that out. Sine theta sine 0. If you do the math, you will see that you have 0 in this case. So sine theta 1, sine alpha 1 in this case, it is 0 minus 90. If you find that out, you see that you have minus s1. That will be minus that's minus 1. So that's minus s1 in this case. So for AI c theta 1 in this case, c theta I in this case. So the theta in this case is 0, so cos 0, and A in this case is 0, so 0 multiplied whatever you have here is 0 in this case. So the same thing for this, the same thing for this, So with that, you get all of these values back. So that is for the sub matrix of this row. So you're going to do for this row also. So you're going to get for this. I'm going to do for this row also. You get for this. So the next thing you'll be doing is you just do your matrix multiplication. When you're doing your ENG 301, you've done matrix multiplication. So because matrix is associative, so what you can do is multiply matrix A1 by matrix A2. Then what you get, you now multiply with matrix A3, because this is your A1 for this transformation 1, A2 for this transformation 2, A3 for this transformation 3 using this model. So if you multiply row times colon, this row times this 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 colon for this, and this row times this colon, this row times this colon, this row times this colon, this row times this colon for this, you'll get these values back, using the models. And what you just do is to multiply this here with the third sub-matrix of the forward matrix, and you get your overall transformation. So if you now sub all the values for your theta and your alpha into this is what you'll be getting at the end of the day. So this is showing you the forward transformation of that robot arm. Now, we already said that the first 3 rows, 1, 2, 3 is your rotation, while your translation is your last colon. The first 3 colon is your rotation, while your last colon is your translation. So this is what you are having at the end of the day. So this is just the model of this. This is the forward kinematics model of this particular robot arm. So you can try out the DH parameters for all of these exercises that you have here and see all the axes are already labeled. So it makes it easy. You can just try it out and see what you have for the DH parameters. So for the inverse kinematics, we already said that inverse kinematics is the opposite of your forward. So inverse kinematic problem in this case is to find out what joint angles would give you a certain position and orientation for your 2 points that you have in mind. And there's a difference between inverse kinematics and the inverse kinematics problem. And we already said that for inverse kinematics, you will have several solutions. I need to test those solutions to see if they would solve your problem. I mean, by getting you to that point and that position and orientation that you have decided in your mind or not. So what is the inverse kinematics problem? Because your 2 points, operates in the Cartesian space, your 2 points will be in coordinates x, y, and z. So it operates in orientation matrix and position vector. That's what your 2 operates with. However, your joints operate with angles. So the inverse kinematic problem is to convert the position and orientation of your manipulator end effector from the Cartesian space to the joint space. So inverse kinematic problem is to convert the position and orientation of a manipulator end effector from the Cartesian space to the joint space. That is what is called the inverse kinematics problem. And we already said that there are 2 methods by which you can solve it. Is the geometric and the algebraic methods. And under the algebraic method, you have 2 other methods. You have the analytical and the other one that we talked about earlier. So, but we'll be doing that in the next class. So thank you very much.